Yeah, today we want to talk about a proper bushing assessment for power transformers, and I think as most of you are familiar that the bushings are the most critical components of your transformer, or one of the most, and we see up to about 22% of the major failures on high voltage transformers related to bushing failure. And of those, about half result in catastrophic failures. And these are explosions, fires, or oil spillage. And, it's well known in the industry that a transformer itself will outlast the bushings at least 2 to 3 times over. The key to, not having these catastrophic failures is to know when to replace the bushings. And that depends on a number of different things. The integrity and the thoroughness of your routine testing or monitoring process is very important. But what we do know is that just based on certain criteria, that there's no common age theory or theoretical age relative to when we can expect a failure. So today, most of your power transformers will have at least two sets of bushings during their lifetime, and sometimes three, depending on the condition. We see transformers now, if they're well taken care of and not overloaded, lasting 50, 60 years, sometimes even longer. And at that point, under normal conditions, your bushings will have a life expectancy of about 25 years. But our experience suggests that, there really are 2 points of failure within a lifetime of the bushings. So when a bushing, let's say, reaches age 10 to 13 years, failure at that point can be possible due to either design of the bushing itself or how the transformer is operating and potential quality issues. Even though they're not aged out in the life cycle management of terms. But when a bushing reaches 20 to 30 years of age, and that's considered the normal lifetime, they're more prone to failure merely just because of age. So while bushings can fail before reaching the age of 10 years, it's also true that they are installed in transformers that are more than 50 years old. So if you're just using age as a determining factor when to replace bushings, you could get yourself into big trouble. And of course, we want to avoid costly replacement of bushings based on age alone, not due to their real condition. So while detecting, upcoming faults, it's essential to know the failure mechanism and failure causes behind the bushings. Why do they fail? What causes them to fail? How can we, early detect the possible failure of a bushing? And we know that design types and manufacturing processes really has a significant impact on the lifetime of the bushings as well. So just a quick review, what is what is the overall principle of bushings? Well, they're the interface components that allow electricity and energy to pass through a barrier to the inside of the transformer. And of course, this is true for bushings on anything, bushings on circuit breakers, bushings on reactors. But the core is usually made of, aluminum or copper, and it's properly sized to carry the current from one side of the barrier to the other. The center core is contained in an insulation system that's, covered with an insulator. And we know that bushing insulation systems of 26 kV and below are designed using solid materials such as porcelain, silicone, or resonant composite. But bushings rated greater than 26 kV need layers of conductive materials, as we see here in the diagram. Conductive materials or foils interspersed with layers of paper to distribute voltage stresses and to minimize large voltage gradients. These layers of conductors and insulation form concentric capacitors between the barrier and the center core. Now, what are some of the common failure issues surrounding bushings? Well, the first and foremost, we want to talk about insulation degradation, aging, moisture ingress, thermal stress, electrical overloading, all weakens the insulation within the bushing, leading to a breakdown of its ability to withstand the voltage. You can have mechanical damage, things like wind, seismic activity, improper handling during installation can physically damage the bushing, compromising its integrity. Contamination, the presence of contaminants, excessive moisture, corrosive substances. If you have bushings in a petrochemical or in a harsh environment, this will also could create contamination issues and lead to premature failure. Partial discharge or electrical sparks within the bushing, and they can indicate early signs of insulation breakdown. And if you leave these unchecked, this can lead to catastrophic failure. Short circuit shocks. Repeated short circuit events can stress the bushing's internal components, potentially leading to installation failure under normal operating conditions. And down here in Florida, where I live, we're the lightning capital of the world. So if you continually expose bushings to lightning or overvoltage conditions due to lightning, that can cause insulation breakdown as well. So if we look at the impact of operating conditions, your operational environment has quite a lot of influence over stress on these electrical assets, and some react different, different stresses. But over the years, transformers have improved in design. We know that. Let's talk about transient voltages or through faults. We know that certain types of transformers can handle transients better than others, core form versus shell form. Um, Local overheating, especially due to bad contacts or overloading, can be another factor for degrading bushing health. Changes of load conditions, especially for the air insulated side of bushings, which are connected to overhead lines. This is result in changing mechanical forces, pulling on bushing heads, through faults. We talked a lot about, I think not last time, but the time before that, we talked about the importance of through fault monitoring on transformers, because through faults that go through the transformer, okay, will put a lot of mechanical stress on the windings and the physical structure of the transformer. Well, the same is true for your bushings, and monitoring through faults. It's interesting because pretty much every new digital relay system has the ability to monitor through faults. What I find in the industry is very common that people don't enable this or pay attention to it. And it really should be something that you should be paying attention to. Um, Electrical transients, they're short bursts of energy introduced into the network, which results in short-term overvoltages. And it could be, just several nanoseconds or hundreds of microseconds, depending on the duration. Three things about transients that you have to be concerned with. Number one is the magnitude of the transient. Okay. Number two is the duration of the transient. And number three is the number of occurrences that you have in transients. And this is why monitoring these things are very, very important. Okay. If you're under a breaker failure condition, that through fault duration is going to be much longer than it normally would be. If you have a slow breaker, transients can be very, very damaging, both to your bushings and to your transformers. But we know that bushings are designed based on your BIL, or your basic impulse level, and that representing the lightning impulse level, actually. And IEC 60137 or C57 1901 has information regarding to the correct BIL. And bushings need to be sized properly for the type of size of the transformer and the type of load. But lightning transient stress, as well as switching transient stress for bushing, seem to be well covered by that standard. So that's a good source of information. The maximum amplitude of transients can be effectively controlled, of course, by using proper surge arresters. High temperature is another thing. So high temperatures due to overloading or overheating of bad contacts can cause a bushing insulation material to degrade a lot faster than it should. For RIP, your resin impregnated paper bushings or resonated impregnated fiber bushings, the glass transition temperature determines the maximum permittable hotspot temperature. So the glass transition temperature is a material property which can be influenced by the resin system composition. Okay, and this is usually below 130 C and below 140 C respectively. So high glass transition temperatures lead to higher bitterness in the material, and it tends to create little micro cracks, which can lead to partial discharge. So to lower glass transition temperatures limit the maximum allowed hotspot temperature. So we can see here in the graph right here, the aging acceleration factor. And we're talking about normal craft paper right here. And you can see in terms of the aging acceleration factor, okay, this is not life expectancy here. This is the acceleration factor of the aging, and the hotspot temperature has a distinct correlation in it as well. So mechanical stress. So additional loads, typically snow and ice, okay, can contribute to the static loads along with seasonal and temperature related variations. The changing load current of an overhead line will result in different temperatures of the wire conductor itself and result in different quasi-static mechanical force. So transient mechanical forces can also be introduced by wind and, once again, through faults. Okay. So in terms of mechanical stress, the bushings are designed to withstand static and transient mechanical forces, but nonetheless, excessive mechanical forces can mechanically destroy a bushing. I know one thing here in Florida that, when we've had, pretty strong tropical storms or hurricanes, some of the bushings will take take a beating, and this puts an absolute, and it may not clearly be evident right away. You're not going to get imminent failure, but it's going to weaken it to the point where eventually it could be a potential hazard. So your forces and transient forces do have the potential to weaken not the bushing, it's just the bushing itself, but the sealing system, okay, of the bushing. So in this particular slide right here, we see, of course, a pretty intense mechanical failure. But even the slightest cracks in a bushing can lead to moisture ingress. And the moisture would, in this case, presumably stay between the bushing core and the inner porcelain or inner composite insulator surface. And the moisture will, over time, mitigate into the condenser core as well. But before that, it can also result in a breakdown along the inner insulating surfaces. So let's talk first of all about some general field tests, and we'll get into this a little bit later towards the end of the presentation. But having a good eye when you're doing an inspection of bushings is really the very first step to look for potential problems. Things such as your terminal taps and connectors, you have to check for tightness to avoid poor contact and heating. Capacitance taps and power factor electrodes, you need to check to determine proper grounding for the bushings with a grounded capacitance tap. And those are the taps, of course, we use for power factor testing on the electrodes. And then examine for proper gasketing to prevent moisture intrusion. Cement, check for crumbling or chipped cement and repair it as required. Gasket deterioration is a huge problem. And it's funny, I was talking to a colleague just a couple of weeks ago, and he went on site to on a recently commissioned transformer to determine why the differential relay tripped. And when he got on site, two things. The first thing he noticed was that all the bushing clamps that were on the top of the bushing were all loose. They were all just hand tightened. So, they weren't properly torqued down. The second thing he noticed was that they had a rolled CT secondary, which has nothing to do with the bushing. It's just a bad practice in terms of, hooking up the connections. And the other thing is that the de-energized tap changer switch was halfway between one tap or the other, which could have been really catastrophic. So, we just have to be very, very careful to make sure we're following proper procedures. But gaskets is a big thing. And the one thing I do want to say about leaking gaskets, if you see oil coming out of the gasket of a bushing, okay, you can darn well guarantee that moisture is going in. Okay, anywhere you have oil leaking out of the transformer, moisture is getting in, and you could very well have a moisture issue. So your metal pads, check and paint as needed. Examine structural parts such as clamp rings and washers. Look for cracks and breaks, and any solder seals. Check for cracks and repair if necessary. So the one thing I really want to talk about today, and this is one of my favorite topics because I talk about it all a lot, along with my colleague Brian, who's coming up last today, and that is moisture issues. Because moisture is a bushing's worst enemy. As a bushing ages, gaskets lose their ability to seal, and they pave, thereby paving the most common way for moisture to get into the bushing. So if moisture is allowed to enter the bushing, it's going to start to break down the oil and paper insulation system, just like it would in a transformer. The breakdown forms various polar compounds and acids that actually eat away and attack the paper. And as that paper breaks down, more contamination is formed. And at some point, two or more conductive layers will break down and short together. And then when that happens, the remaining concentric capacitors will have a larger voltage stress across each capacitor. So as the breakdown goes unchecked and moisture continues to enter the busher, the rate at the contamination is being generated inside the bushing naturally is going to increase. That causes the layers to fail. And at some point, there's going to be a catastrophic failure of the bushing. So your risk increases dramatically with age and voltage level. So bushings rated greater than, let's say, 230 kV or older than 25 years fall into this highest risk category. And the next lower risk category compromises bushings, between the 100 and 230 kV, older than 35 years. So the higher the voltage rating of the bushing, the longer it's been on the transformer, the more susceptible it's going to be to moisture contamination. So we know that if moisture ingress is the leading cause of bushing failures, there's good news and that there is a way to evaluate the deterioration of the bushings insulation system. So again, moisture can be in bushing can be caused by several situations. Leaking gaskets due to mechanical stress or aging, with the most common cause for allowing moisture to ingress into the bushings. Moisture can be found in the insulation paper or the oil. So when it comes to moisture, your OIP bushings behave pretty similar to transformers, with the difference being that within that condenser core, the oil can't circulate that freely. When you have moisture in a transformer, it's constantly being circulated. Okay. And the amount of oil versus the moisture in the oil versus what's in the transformer itself in terms of the insulation, the solid insulation, depends greatly on the operating temperature. But since it can't circulate in a bushing, that means that moisture slowly creeps into the bushing. It'll initially remain outside the condenser core and within the outer layers of the core. So over time, the moisture will ingress further into the bushing. So it's important to understand that the aluminum layers are also slowing down the crosswise distribution of the moisture. So moisture will likely impregnate lengthwise into the bushing core. So since moisture can't really impregnate pure resin, the moisture in an RIP bushing will be found strictly in the paper. So comparing RIP bushings to OIP bushings, cores, the resin will provide an additional barrier against the crosswise moisture impregnation. As for the OIP bushings, the lengthwise moisture impregnation will be the major way for moisture to mitigate into the bushing. So besides leakages, RIP bushings can also get wet due to improper storage. Now, we had a customer that was storing these RIP bushings outside in a crate for quite a few years. And when they went to take them out of storage and use them on a transformer during a bushing replacement, it was determined that every single one of them, we're talking about 25 different bushings, were all bad because the moisture had been impregnated into the bushing itself. So lesson learned, store your spare bushings properly. Don't allow moisture to get in. Okay, so how do we test for moisture? Well, how do we test for the general health of bushings as well? Well, the first thing that we all know, one of the tests that we do is, of course, power factor testing. So insulation power factor tests are used to measure dielectric loss. And that can relate to wetness, dryness, deterioration of high voltage insulation, and leakage current. Okay, in a bushing is compromised to two components. You have resistive current and a capacitive current. So in practice, no installation really is perfect, but it has a certain amount of loss, and the total current leads the voltage by a phase angle of 90 degrees. Again, it's just basic fundamental power factor knowledge. But power factor and capacitance measurements of both your C1 and C2, okay, are performed sharing the same test setup. All the bushings on each side of the voltage level of the transformer should be isolated and shorted. All groups of untested bushings should, of course, be grounded. But a C1 power factor dissipation power factor test checks the health of the bushing's main core insulation, while your C2 test measurement is used to assess the bushing's tap compartment's insulation, plus the outer main core insulating wraps around the surrounding filler material. So I know that a lot of people don't typically or may not typically do a C2 test, but a C2 test I would consider to be very important. And one of the reasons I think that it gets overlooked is because a lot of your bushings don't have any C2 nameplate data. So we'll talk about that in just a bit. But why do we test bushings with power factor? Well, we want to look at the insulation condition assessment. And that is, power factor testing will help identify things such as aging, deterioration, moisture ingress, or anything that can lead to bushing failure. And this, of course, will help prevent your catastrophic failure. And we know that bushing failures can be damaging and costly, obviously. Optimizing maintenance. So by identifying which bushings are healthy and which require attention, power factor tests allow for more efficient allocation of resources and planning outages. They're often equipped with a test tap or a voltage tap or potential tap for power factor measurements. So it shouldn't be that difficult. Even if they're not, we can always perform what's called a hot collar test. So it involves applying a high voltage to the bushing conductor and measuring the leakage current, and the power factor itself. So for bushings without a tap, again, as I said, you could always use a what's called a hot collar, or a thing that looks like a rubber band that goes around the porcelain on the outside of the bushing to actually do the measurement. Another thing we like to do is what's called a tip-up test, and that is measuring the power factor at various voltage levels and making sure you're getting the same results. Okay, so if we look at the bushing, it's kind of divided into two parts. The innermost insulation of the system is made up of these several concentric capacitors, and we refer to that as C1. The outermost insulation of the system has only a few layers, and that's referred to as C2. So the main purpose of the division is to allow a test connection point for offline electrical tests. And normally C2 is shorted out by the cap cover when the bushing's in operation. Very important. Now, in rare cases, for bushings rated 69 kV or greater, this point is used to feed a potential device. So it's possible because C1 and C2 are not influenced by external factors such as bushing turn or tank walls. So in other words, a bushing can be used as a reasonably accurate capacitor divider to feed a potential device for measuring the voltage that is being applied to the bushings. So on bushings that allow for external potential, the tap is referred to as a potential tap. So the potential tap can easily be spotted because it's got this stud when you here that you can connect to when the bushing tap cover is off. The other type, the potential tap or test tap can be used for, both of them can be used for testing. But on this particular, you'll see a spring. And actually, when the tap cover is on here, the spring is grounding out this tap. So either of these two are suitable for measuring power factor. Okay, so there's a couple of different tests that we want to run. So high voltage bushings that have the tap cover, we're going to do a C1 and C2 test, as measured from the tap to the grounded flange. You have to perform your power factor tests on each bushing equipped with the tap. And in the absence of the tap, we're going to use a hot collar test. There's various types of tests. An overall tap, the center conductor to the flange. Typically, your C1 is going to be an ungrounded specimen test, or UST, from the center conductor to the tap. You can invert that, okay, from the conductor back up to the tap, and then tap insulation test. I've got a figure. This kind of illustrates it a little bit better. Here you'll see your connection diagram for a C1 test, where we're going to the top of the bushing down to the and measuring here at the tap. And then, of course, your C2 test, and then a hot collar test as well. So if the best use of how we're going to perform these tests is available through certain IEEE standards. C5719-100 will indicate that a progressive increase in power factor or change in capacitor of 5% or more warrants investigation. Now, I didn't say change it out or take it out of service, more investigation. C57-152 suggests more frequent testing for bushings with power factor increases from 1.5 to 2 times the initial reading, and the removal of service if it triples the initial reading. If we take a close look at what these guides are telling you, you can see this right here. So general guidelines for evaluating the C1 power factor test look as such. If the power factor measures up to twice the nameplate rating, that's acceptable. So if it's at 0.23 and it's showing 0.4, that's okay. But between twice the nameplate and up to 3 times, that means you want to monitor it closely. Now, if you don't have a bushing monitor or an online monitor, that means that you may want to increase your, or decrease the time to where you're going to go, test it once again. If it's 2 times up to 3 times, that means you're definitely going to replace that bushing. So in evaluating the capacitance, okay, basically we're going to look at the nameplate capacitance of being plus or minus 5%, which is acceptable. 5% to 10% means, again, monitor very closely. And then anything greater than 10% means you're going to replace that bushing. So elevated changes in the C1 tests are usually contamination issues, and that's caused by oil contamination or breakdown in short-circuited condenser layers. Changes in C2 power factor, which again is not always included in the nameplate, are most commonly indicative of oil contamination. So what do we do if we don't have a nameplate for C2? How do we know? Well, the most important thing is, when you commission a transformer, to get a C2 baseline. Baseline is very, very important. Okay, then you have a starting point. If you don't have a baseline, you can you do a C2 test on all the bushings, and all the same bushings should be relatively the same. If one is elevated over the other, or 2 out of 3 are elevated, then that might be suspect. Okay, but don't skip the C2 test. Very, very important in terms of assessment. So, one of the things that I want to bring to light, and I think this is very, very important and something that really gets overlooked, because I know it gets overlooked because I rent test equipment. And when I see people rent various types of test equipment that can only do power factor at 60 hertz, I know we're missing the ball on this technology. So, and this is also very applicable to doing power factor testing on a transformer as well. So basically what we want to do is we want to find equipment that can actually do power factor measurements at variable frequencies, say from 10, 15, 30, all the way up to 400 hertz, and get measurements at these different frequencies. Because in general, if oil and paper insulation system is healthy, the measured power factor value increases versus frequency. So in other words, the frequency trace climbs uphill versus frequency, and this is normal. But as your oil and paper insulation system deteriorates, the frequency sweep trace typically becomes flat or even worse, and this decreases versus frequency. So if the trace decreases versus frequency throughout all or most of the sweep, the installation system is typically considered questionable and may require further investigation. But another characteristic that we see that's very distinctive is what we call the fish hook. And that is when in your 1 or 10 to 60 hertz power factor measurements shows a much higher value. What that's indicative of is what we call are what we call conductive losses. Now, what is a conductive loss? Well, in a power transformer, oil-filled transformer, it could be sludge, it could be furans, but for bushings and transformers as well, it could be moisture intrusion. So the shape of the frequency sweep traces between all your bushings should be reasonably similar when comparing similar unit bushings. So the shape of the trace of one bushing, if it's dissimilar relative to the shape of the other, then that dissimilarity should be considered something that needs to be investigated further. Okay, now here we see a frequency trace, a C1 on a C1 measurement of sister bushings that are provided, that we see here. All three bushings have the same geometric shape going from 10 to 400 hertz. There also has a lower power factor between that 10 and 60 hertz range. Now, that would indicate that we have no significant conductive losses. So you're relatively safe in assuming that there's dry insulation within the bushing. Okay, so here's a case study. I got a couple of case studies I'll share with you just to finish things up. But what we saw here was your power factor measurements at 60 hertz compare well to the nameplate data. Okay, and you'll see here we did a tip-up test. Okay, we did a tip-up test for all three bushings. They're well within range. Okay, and they're all in fairly well within range of the nameplate data. Okay, with a slight difference in H3 and a slightly elevated difference between the nameplate rating. Okay, now, if we look at our variable frequency test, all right, you can see quite clearly that the H3 bushing has a much higher power factor value in that lower range. Now, what that would tell me, okay, if I was doing an analysis on this, H3 should be looked at much more carefully and should be, you know, probably retested again at a later time, and just to make sure that, we're not going to have a problem. But of the three bushings, the two H1 and H2 look just fine. H3, that's going to raise some suspicion in terms of going down the road for further maintenance testing. So when comparing the power factor in these traces, um, well, interestingly, at 10 kV, the power factor H3 is below 1.5 to 2 times its nameplate value, which, if you look at the industry standards, that's considered acceptable. But when you see this fishhook approach, okay, that would tell me that that should be flagged as a weak link among the three bushings. And if you're going to return it to service, it should be tested more frequently to gauge the severity of the situation. Okay, so here's another case study that was done on a lap bushing. And in this case, the 60 hertz power factor was already showing extremely elevated measurements in H3. So we knew that one's got to go. All right, but let's take a look at the other two. On the other two, okay, again, we see kind of within range. Your tip-up test had a little bit of variance on H1. Okay, but if we do, again, we look at the variable frequency results and we see that H1 is is elevated again. And that would also indicate that, we should take a better look at H1 going down the road. Okay. Here's a really good one. Okay. This is crazy. I mean, you look at these traces and they make no sense at all. But you'll see H1, it is fairly normal. H2, okay, is got that fish hook. So that would be indicative of some moisture ingress. But H3 doesn't show a fish hook, but look how elevated it is at the higher frequency. So there appears to be a bushing insulation failure mode when measuring the capacitance of a bushing that's dissimilar relative to its nameplate data. And remember what I said. You want to see on good, healthy bushings, all three appearing the same. But interestingly, H1 and H2 tested with capacitance value well below their respective nameplate values. But the capacitance value of H3 bushing is above its nameplate value. So if the measurements provided in the illustration can be verified, and verified by meaning did I do the test properly, the insulation system of H3 bushing is definitely suspect. And if return to service should be investigated further. Okay, now this one was totally out of whack. Okay, this is again case study 4 on a lap 138 kV bushing. And you'll see here that based on the power factor values of all three bushings, the results are higher than their respective nameplates. Notice the power factor measurement on H2 bushing is clearly voltage sensitive. Furthermore, the power factor frequency sweep traces for the three bushings are very erratic. So in general, jagged power factor sweep traces are indicative of an invalid power factor measurement. So regardless of whether the insulation system is healthy or compromised, this the frequency sweep should be smooth. It shouldn't have any kind of jagged thing like that. So well, in this particular case, the customer determined that the primary side bushings of the terminal were not shorted together when C1 power factor measurements were performed. So lo and behold, you could have looked at the 60 hertz values and said, "Oh my gosh, H1 and H2 look, H1 and H3 look okay. H3, nah, that's way out of whack." But in this case, the frequency sweep tells you you just didn't run the test properly. Okay, now another thing that I want to touch on, and we'll finish up very soon so we can get some questions, is one of the things that's very important is, of course, your dissolved gas analysis on your high voltage bushings. And of course, we do this in transformers, and it's very, very important, of course. But basically, oil sample collection is representative sample of the insulating oil, and it's carefully collected from the bushing following procedures to prevent contamination. Um, Gases dissolved in the oil are again extracted using methods like vacuum extraction or headspace analysis. Your gas analysis are analyzed using the chromatography to identify, just like your transformer. Taking oil samples of your oil filled bushings are just as important. And what we want to look for, again, if you see indications of any of these particular gases, such as hydrogen, you've got partial discharge, arcing and overheating, methane, low energy arcing or thermal faults, ethane is a result of overheating and thermal faults, as is ethylene. Acetylene, that's going to be the bad one. That's arcing in the oil where very high temperatures. And then CO and CO2, of course, is your insulation degradation or oxidation. And it is very, very similar to what you see in a transformer. So there's some benefits to doing, of course, a DGA, and that is early fault detection, condition-based maintenance. A DGA enables maintenance based on the actual condition of the bushing rather than a fixed schedule, um, you know, which could reduce your costs and downtime, improving reliability and safety. Um, Trending analysis, again, trend analysis for DGA, just like in a transformer, is very important for your bushings. When do you do it? Well, when do you do DGA? Well, the first and foremost, you should do it on new bushings so you can get a baseline. It's always recommended. Routine monitoring. Annual testing is recommended for routine monitoring. You should shorten that period on critical bushings. Okay, if you have critical assets, GSUs, or depending on the conditions. Okay, if you're in a high caustic environment, or if you're in a very weather related incidents are common, then you may want to increase that frequency of testing. Event-driven testing. This is also important. If you ever get some type of an abnormal operation, or your protective relays have tripped, also good time to do a DGA. Okay, another very popular way to look at the health of bushings is through your thermographic inspection. In addition to your visual inspections, your high voltage bushings can be examined with infrared cameras. If any of the bushings are abnormally hot when you're compared to the unit under similar loading, there's probably a loose connection, like we talked about earlier. And the good news about this, of course, you want to do it while the transformer is online. But it's not uncommon to find problems with the connection at the top of the bushing. But a defective connection inside the transformer tank can also show a higher temperature at the top of the bushing. So bad connections may not always be the case of the heating, but that is usually the case. Okay, now another test that is getting more and more popular is looking for partial discharge. And that is partial discharge, again, is a localized electrical discharge that doesn't completely bridge the insulation between conductors. It's a symptom of insulation defects like voids, cracks, or contamination. We do PD testing on cables all the time to look at the health of the insulation. We do it on transformer windings. We do it on motors. We do it on generators. PD is becoming a very, very popular test in terms of getting that first indication of insulation problems. And your PD measurements on transformer bushings, the good news is you can do it either online or offline. If you're doing it offline, of course, you need a voltage source to energize the bushings, which can sometimes be a little bit difficult. So again, visual inspections, look at the porcelain for cracks or contaminations, look for oil leaks. If your oil level never changes, even with a wide range of ambient temperature, there's a pretty good chance your gauge is stuck. Okay, so look for that as well. Low oil levels could be corrected by checking your mounting bolts for adequate torque, inspecting the gasket. Again, I've seen people that have done bushing replacements. They didn't torque the bolts down good enough, and water was just rushing into that transformer. So when you're doing a bushing replacement, just make sure you use a torque wrench and you torque those bolts down appropriately. And gaskets with poor seals are probably also leaking water and air into the transformers, and that'll show up in your DGA or your DFR testing. Check for tightness again on your contacts on the top of the bushing. Look at the tap covers. Okay, I've taken tap covers off to do testing and found them filled with oil. Make sure that the gasket around the tap cover is solid and has a good seal, and that you tighten that down correctly. So tightness is an important thing. Now, cleaning. Everybody asks, how do I clean a bushing? Well, it's important to clean the bushings, not only to get accurate power factor measurements, but also to improve the durability of the porcelain. And sometimes you have to be, depending on the environment, you have to, high pressure water to clean them, or limestone powder blasting. But the one thing that's always good to clean your bushing is use a good silicone wax designed for cleaning bushings. Okay, it doesn't change the thermal temperature of the porcelain, so it won't affect your test results, and it puts a nice protective layer on the bushing itself. Now, one final word about online bushing monitoring, and my friend Brian, I'm sure, will tell you all about this. And what's really nice about online monitoring is that it gives you a consistent evaluation of the bushing health. Um, and you will see times where maybe the bushing monitoring will give you different results than doing it offline. Well, why is that? Well, you're under normal operating conditions at temperatures that are normal. Um, and this makes failure modes a bit easier to detect online while the transformer is energized at operating voltage. Okay, online monitoring can detect incipient faults that are not detected by offline tests. So a fault's development time is typically less than the time between offline test cycles. Online systems measure the performance constantly, and since these test parameters are different, the results may be different. Now online monitoring may not always be economically feasible in all cases. You talk to customers, hey, I got 480 transformers out there. I can't put a monitoring system. Well, then you better make sure your maintenance testing is well defined. Okay. If you take a guy that sells transformer test equipment and a guy that sells monitoring systems, they'll have a 2 hour argument and a Jerry Springer fist fight eventually. But for most cases, both are very appropriate. Okay. Just a couple of references: C57-152, Guide for Diagnostic Field Testing of Power Transformers; C57-141, Guide for Detection, Monitoring, and Evaluation of Winding Deformation. There's also a new guide out for monitoring systems from IEEE, as well as the field guide for testing has also been updated as well, and is due to soon be released. And Farad will talk about vibroacoustic testing of LTCs, and that's also contained in the new IEEE guide for field testing of oil field transformers. So the resources are out there, people. I encourage you to use them and implement them into your maintenance programs. So, Randy, we'll take
Okay.
questions.
Yeah, great. Thanks very much, Drew. Yeah, I do have a few questions here. You mentioned that transformer bushings are responsible for up to 22% of major transformer failures.
Mhm.
Why do you think bushing failures are still so common, despite the advances in testing and monitoring? And is it really 22%? I thought it was more like 40%.
Well, that was the latest data that I came up with, and it may be
Hmm.
higher.
Yeah.
And I suspect, yeah, maybe it is higher, because if you have a catastrophic failure and you're left with a pile of molten lava at the end of the day, it's kind of hard to determine. Exactly. But number one is the exposure. There's nothing surrounding the bushing to protect it. It's not encapsulated in a tank like transformer windings are. um, Design is another thing. There have been design issues and manufacturing issues that rear its ugly head. And that happens quite often. But the exposure to transients, to lightning, to you know environmental conditions, um, and again, lack of proper maintenance and testing, I think is certainly key.
Are there fewer transformer failures because of all the monitoring, periodic testing, and online monitoring taking place?
Well, that would probably be a good question for Brian. That's his his
Well,
his specialty. But
I it's an extension of that question, right?
Yeah,
With all
e-
this bushing monitoring and
exactly.
testing, are there
Yep.
fewer failures than in
I
the
would.
past?
I'll verbally answer that one. I'll contribute to that one. Those failure statistics that Drew, I think you were using, arrived from a Seagray
Correct.
survey of bushing. There's a great document that Seagray produced on bushings exclusively, and with multiple pictures of failed bushings and why. And so those statistics come from the survey that was done within the working group of Seagray, and I forget how many thousands of bushings were involved, but
Yeah.
that's where those statistics come from.
Yep.
And it's interesting when I've been involved in monitoring for 20 years or more now. The Yes, some transformers are equipped with bushing monitoring, and yes, some bushings do fail. And it's been my experience that when you go out and ask the nasty question, not nasty, but embarrassing questions to customers about, well, the monitor, my records, I download the data, and obviously there was an alarm, and here, time and date. What did you do? Well, we didn't know because nobody connected the relay alarm contacts on the monitor into SCADA or into a data acquisition system. And some people, the transformer person says, that's not my job. That's the SCADA guy's job. Unfortunately, that's really, I mean, that has happened. And Drew, you've probably seen that before
Oh,
yourself. Yeah.
absolutely. Yeah.
The
Yeah.
other thing is, and I'll cover it a little bit in my little talk, but when you have monitors, you need to have an action plan. When an alarm does come up, what are you going to do and who's going to do it and within what time frame are you going to do it?
Yeah. Yeah. It's not a smoke detector that you just hit the silence button.
Some
Right?
people have done that and hit the reset button and said, okay. And then, that's when smoke gets outside the tank.
Exactly. Thank you,
Yeah.
Brian.
Okay.
Thanks, Brian. Thank you, Dr. Sparling. All right. Next question. For someone managing a transformer fleet, how can they prioritize which bushings to test or replace first without relying solely on age?
And that again is a very good question, because when you have a strictly time-based maintenance in terms of when you're going to replace a bushing, you're going to get into trouble. And in terms of, maintenance testing, annually checking for bushings. And that's why we want to dig a little bit deeper. That's why this variable frequency power factor measurement can be so valuable in terms of, you know, closing in that cycle a little bit more. I mean, that fish hook tells me this bushing is probably going to fail before the other two. Okay, it's showing a problem, it's showing an issue. And what's surprising to me, because variable frequency power factor testing, and DFR as we know it, dielectric frequency response, has been around for a very long time. But I can tell you, based on the equipment that we rent to our customers, it doesn't get utilized nearly as much as it should. Um, and I can't figure out why. I think maybe over in Europe it is a bit more prevalent in terms of doing testing. But you've got to look at all the signs. You've got to look at your dissolved gas analysis on an oil field bushing. You've got to look at your variable frequency power factor, your C1, C2. You've got to pay attention to any abnormality that you see in your test results, because it's not going to say, oh, I got to replace this bushing because it's more than 10% off. It's, am I seeing an indication that this has a potential for a problem? And that's the most important thing.
Okay. Next question. How can power factor testing help a non-specialist like me understand whether a bushing is nearing failure? Are there simple signs or thresholds I should consider or I should watch for?
Yes, and that is again referring to your IEEE guides and standards.
Yeah.
And that's easy. I mean, just go to Google, type in IEEE standards for bushings, and all that information is there. How much deviation represents a problem.
Mhm.
What is my DGA telling me? What my variable frequency power factor is telling me. You got to do a little bit of research. The standard is there in terms of, am I seeing something good or seeing something bad? And Brian will tell you, I mean, we work hours and hours and hours out of the year to develop and publish standards in the Transformers Committee. And I've been doing it for 8 years. Brian's probably 3 times that. But, the amount of work that we put into this, and people don't utilize it enough. I can tell you right now that, if you go out and ask, 10 NETA technicians if they know what dielectric frequency response is, they'll probably 9.9 of them will tell you, no, I never heard of it. When that standard's been around since 1997, I think it was first developed.
Mhm.
So, do your research. Um, Take this
Oh,
presentation. It's got some good guidelines in it.
good. May wants to know, normally the testing of a transformer is completed by its suppliers and finished before shipping to sites. Could you recommend some brand transformer manufacturers? Well, I don't know.
Now, without
May.
getting into trouble.
May.
Now, and that's it's
But
important.
it's, she brings up a good point that
Yes,
the transformer manufacturers, before they sell the transformer and they ship it,
yes,
they do basic testing on it, correct? And they
yes. That,
provide those test results to
yeah,
the owner
yeah,
as a
and
starting point.
it doesn't start. I mean, sweep frequency response analysis is the one, of course, you want to specify to have done before it ships, because it's going to look for any mechanical deformation during the shipping process. Another one that and I think it doesn't stop at the factory acceptance test. It stops with proper commissioning.
Mhm.
And we could have a whole nother topic on what to do when you're commissioning a brand new transformer. You should always look for moisture, do dielectric
Mhm.
frequency response. You should do a leakage reactance or short circuit impedance to make sure that the impedance stamped on the transformer is true and accurate.
Mhm.
You should do a DFR. I mean, there are a whole battery of commissioning tests that are very, very important. And a lot of that also helps you establish baseline. And on bushings, if you don't have a C2 standard or a C2 stamp on that bushing, I would definitely do a C2 test and establish that
Mm.
baseline.
Okay. Okay, good presentation.